Section 5.3, Exponential Functions. I want to start with an example where you're given a graph and you're supposed to determine the exponential function whose graph is there, mainly because I don't like the book explanation or the video explanation. I think it's really way too complicated for what you need to do. Okay, so if we are going to write an exponential function, we know it's of the form c to the x, c times a to the x, right? And we can see by looking at our graph here, we've got lots and lots of points, right? We can see that if I plug in 0, right, that's equal to 1, right? So 1 is equal to c times a to the 0th power. Well, we all know that a to the 0 is 1, so 1 times c is just c. So that's telling us that c is equal to 1. Okay. Now, to write the function for this graph, we need c, which we just found is 1. We need a, right? And x is our variable. So how can we find a? Well, we now know that our function is equal to 1 times a to the x, or just a to the x is a to the x, right? So now we just need to find a. Well, we can use any of the other points to help ourselves find it. And I'm actually going to show you using all 3 of the other points that it works out, that, you know, they work out the same. And if they do, it's a good thing to check to make sure that they do, to make sure that you're getting the right function in case you're making a mathematical error. Alright, so I'm going to take this f of x and I'm going to plug in 3 different points. The first one I'm going to plug in is f of 1. F of 1 we know is 6 from our graph. Okay. Oops, sorry, that shouldn't be an x, that should be a 1. So a to the 1. So here we're saying 6 is equal to a to the 1. So this is already telling us our value for a that we are looking for is 6. But let's make sure that it is by plugging in the other 2 points. F of 2 is 36, which will be a squared. And we can see from here that a is going to be 6. It could also be negative 6, but of course we need to make sure that a is always greater than 1. I'm sorry, greater than 0. And the third point that we're going to plug in is f of negative 1. Well, f of negative 1 is equal to 1/6. And when we set negative 1/6 equal to a to the negative first, because we're plugging in negative 1 here, right, we can see, oh, negative 1/6 is equal to 1 over a. I'm sorry, it shouldn't be negative 1/6, it should be positive. Excuse me. We see that 6 is indeed equal to a. So our final function then is f of x equals 1 times 6 to the x, or just 6 to the x. Okay, now for the rest of the video, what I want to answer for you is a question that you might be having. What in the world is e? Right? Well, e stands for exponential constant, right? It's an irrational number. It's approximately 2.718, but it's one of those numbers with an unending, non-repeating decimal expansion. It arises as a growth factor. It's a growth factor in all kinds of finance and natural phenomenon that grow exponentially. Okay, so it's a growth factor. It's a number that gets multiplied multiple times. So where does it come from? Well, we're going to look at a real world problem with a savings account that has $300 principal, compounding monthly, at 2% annual interest. Okay, so the interest is compounding monthly. That means it's being added once per month. And we're going to say a of n is the amount in the account after n months. Right? So let's find out how much we would have after 1 month. Well, a of 1, remember n is months, so a of 1, we would have $300, the principal, plus 0.02 divided by 12. Remember the interest rate is 2%, but that's annual, so we'll divide it by 12 to get the monthly, times that $300 that's there. Okay? All right. Then what we're going to do is say, okay, let's factor out the 300. This becomes 300 times 1 plus 0.02 over 12. Okay, how much do we have after 2 months? Well, a of 2 is going to be everything that's still there, so this is a of 1 after 1 month. But then we're also going to add 2% divided by 12 of that amount, which is 300 times 1 plus 0.02 over 12, right? And I can see, oh, let's factor 300 out of this, right? We have two terms, 1, 2. They both have a common factor of 300. We'll pull out 300. We're left inside with 1 from the first term, 1 plus 0.02 over 12, plus in the second term we get 0.02 over 12 times 1 plus 0.02 over 12. And then we can factor out the 1 plus 0.02 over 12 out of each of these terms. So we're going to get 300 times 1 plus 0.02 over 12, right? Open up the parentheses. We get a 1 left when we factor this factor out of both terms. And when we factor the factor here out of both terms, we're left with the second term, we're left with 0.02 over 12 again. Notice this simplifies to 300 times 1 plus 0.02 over 12 squared. Right? If we look back, we can say, oh look, a sub 1 equals 300 times 1 plus 0.02 over 12 to the first power, and a of 2 is 300 times 1 plus 0.02 over 12 to the second power. So we're going to generalize now and say that after n months, we end up with 300 times 1 plus 0.02 over 12 to the nth power. Okay? Now, we're going to let t equal a number of years. Right? So then over t years, the amount in our account is a of t equals 300 times 1 plus 0.02 over 12 to the 12t, right? Keeping in mind that 12t is counting the number of months in t years. All right, but what if the money is compounded quarterly? Well, we would get a of t is equal to 300 times 1 plus 0.02 over 4 to the 4t instead of 12 to the 12t. What if it's compounded daily? Well, we get 300 times 1 plus 0.02 over 360 to the 360t power. In finance, they use 360 instead of 365 days for a year. Don't ask me why. So now we'll say, what happens if it's compounded n times per year? Okay. So this becomes 300 times 1 plus 0.02 over n raised to the nt power. So, generically then, this was a specific problem. If we let P be the principal and R be the interest rate, right, then we can say that A is equal to P, the principal, times 1 plus R over N raised to the NT power. We're going to rewrite this. We can say 1 plus R over N is the same thing as 1 over N over R to the NT. Okay. And then we're going to make a note here, right, that if I take N over R and multiply it by RT, that's the same thing as NT. Okay, so we're going to replace NT with that. We're going to say P times 1 plus 1 over N over R to the N over R power times RT. This is an N here, and that's an RT. Okay. Now we're going to let a new variable, we'll call it H because that's what the book does, equals N over R. Okay. So that gives us P times 1 plus 1 over H, all raised to the H power, all raised to the RT power. Now what we're going to do is we're going to let H go to infinity. Because remember, we were trying to look for was what happens as it compounds more and more and more, right? This is the idea that the number of times that the interest is going to be compounded, it gets larger and larger every second, every millisecond more. It heads toward infinity. When H goes to infinity, N over R goes to infinity because H is N over R, right? And that happens because as you get a bigger and bigger numerator and with a constant denominator, that number is going to get bigger and bigger and bigger and bigger, right? So what happens then is that 1 plus 1 over H to the H power goes to E, which is the definition of E. Yeah? So we can rewrite this entire thing as P times E to the RT power, because here's our 1 over H to the H going to E, P equals RT. This gives us the formula for what we call continuously compounded interest. And it also shows us a little bit about E.